Enterprise network engineers routinely break their first IPv6 deployments by relying on legacy muscle memory. The failure almost always traces back to a single reflex, attempting to configure routing by defining global subnets. In the IPv4 era, you told a routing protocol which global subnets it should advertise. The router then worked backward, indirectly matching those subnets to its active interfaces. This diagram shows the new logic for IPv6. The routing process completely bypasses the list of IP subnets and tethers itself directly to the hardware ports. Routing is strictly interface-centric. You enable the protocol explicitly on the physical or logical interface itself. This approach gives you exact control over your network borders, ensuring that an unintended subnet is never accidentally advertised to the rest of the topology. All three major interior gateway protocols, RIP-NG, EIGRP for IPv6, and OSPF-v3, adhere strictly to this rule. Success in an IPv6 environment depends on moving architectural control away from the global subnet and down to the hardware link. An out-of-the-box router configured with IPv6 addresses is, from a routing perspective, effectively just a host on the network. By default, its internal routing engine is turned off, actively rejecting any dynamic IPv6 routing protocols attempting to start. To open the gateway, you must execute a single global command, IPv6 unicast routing. This command activates the router's internal ability to forward IPv6 packets and allows it to participate in dynamic routing processes. This diagram shows a router populated entirely with hexadecimal IPv6 addresses, but as it attempts to initialize EIGRP or OSPF, the process fails to start because of a structural requirement, the router ID. Even in a pure IPv6 environment, these advanced protocols mathematically demand an IPv4 formatted 32-bit identifier to track their topology. If there are no IPv4 addresses on the router to borrow an ID from, you must intervene and configure this 32-bit value manually. When an IPv6 routing protocol fails to launch, the cause is rarely a flaw in the protocol itself. It is usually the omission of one of these two foundational global steps. Let's apply this interface-centric model to a standard enterprise topology to see the mechanics in action. This logic flow compares the configuration of RIP-NG on the left and EIGRP-v6 on the right. Despite their differences in metric calculations, they share the exact same configuration sequence. Looking at the left side, the sequence for RIP-NG begins by creating a routing process globally using the IPv6 router RIP command. The actual activation happens in step 2, as the RIP process attaches directly to a specific router interface. Once bound to the interface, RIP-NG begins transmitting its routing updates out onto the wire via its dedicated IPv6 multicast address, FF02:9. EIGRP for IPv6 employs a complex loop-free path algorithm, but its activation sequence mirrors RIP-NG exactly. Defining the process globally establishes the EIGRP routing block, tied to a unique autonomous system number. The EIGRP process block then moves down to attach to a physical interface using the IPv6 EIGRP command. Once active, EIGRP uses its own dedicated multicast address, FF02::A, to discover neighboring routers. This explicit two-step configuration, creating the process globally, then activating it directly on the interface, ensures that routing updates only traverse your intended physical links. When we look at our final protocol, OSPF-v3 represents the most significant architectural departure from its IPv4 predecessor. This setup illustrates the core paradox of the protocol. OSPF-v3 routing packets do not actually contain IP routing addresses. When enabled, link local addresses beginning with FE80:::, are automatically generated on the connected hardware interfaces of both routers. The routers immediately begin exchanging hello packets strictly between these two link local addresses, using the multicast address FF02::5. A successful adjacency forms across the physical wire, despite the fact that their global unicast subnets are completely incompatible. This succeeds because OSPF-v3's neighbor adjacency logic has been decoupled from global IPv6 addressing. The routers only care that they share a physical link. Since the neighbor packets are stripped of global IP data, a secondary mechanism is required to distribute actual routing prefixes. They accomplish this by introducing a new data structure into the flow, the link state advertisement, or LINK LSA. The link LSA is explicitly designed to carry the IPv6 prefix information backward across that established link local adjacency. Relying on link local space for neighbor formation, OSPF v3 simplifies infrastructure addressing, allowing you to build robust routing backbones without wasting a single global IP address. Once the configuration is applied, the focus shifts to operational verification and troubleshooting. In IPv6 environments, missing routes are best diagnosed by verifying interface bindings before examining the routing table. Running the Show IPv6 Protocols command gives you immediate confirmation of whether a routing process is actually active on the correct physical ports. After confirming the interfaces, you inspect the final topology using the Show IPv6 Route command. This output displays a learned OSPF v3 route entry. Look closely at the highlighted next hop address assigned to that learned route. The next hop is an FE80 link local address, not a global unicast address. Migrating successfully to IPv6 requires internalizing this architectural shift. Routers now communicate exclusively with their immediate hardware neighbors, using those localized conversations to build a comprehensive map of the global network.